So in this video, we have a introduction to Riemann sums. So I've got a function f of x equals x squared plus 1. And I'm going to approximate the area under the curve with some rectangles. I'm going to use 3 different ways to do this. Now, first thing I know is I'm starting at 0 and I'm summing rectangles to 3. So a equals 0 to b equal 3. I want to divide this up into 3 rectangles. So I'm going to use n equal to 3 rectangles here. If you divide up and you're going to use 3 rectangles to get the area. So approximating the area with those 3 rectangles or whatever. Then what you need is you need a x1, you need an x2, you need an x3, and you need an x4, okay? And we can call that x1 the A and call that x4 the B. And then we sum each of the areas of those rectangles to approximate the true area under the curve, which might be this part right here, okay? So we're using the area of rectangles to approximate the true area. So if you're going to use 3 rectangles, you need 4 values to partition your interval up into, and that's what these 4 x values are, okay? So to figure out how long to make each subinterval, we take the length of the interval and divide by how many rectangles we want. Makes pretty common sense. If I have from an interval from 0 to 3 and I want to divide it up into 3 pieces, I take what? I take 3 minus 0 and then divide by 3, and that gives me 1. So each of these pieces has a length delta x equals 1, delta x equals 1, delta x equals 1. So the width of each of those rectangles has a width 1. So this x delta x equals b minus a over n is a formula that is used to find the width of the rectangles that you're summing. So there's 3 common ways that you can use Riemann sums. So all 3 of these are Riemann sums. There's a left-handed rule, there's the right-handed rule, and then there's the midpoint rule. And each one of them has an advantage particular to itself. So the left-handed rule, the heights of a rectangle is from the x-axis to the left endpoint of the subinterval. That's why it's called the left-handed rule. We go to the left endpoint of the subinterval. So what do I mean by that? In a picture here, I have my function f of x equal to x squared plus 1. Now the left-handed interval, and remember we're integrating from 0 to 3, so I'm going to have 3 rectangles summing this up, right? So the left-handed endpoint would be this endpoint right here, right? The left-handed endpoint for the next one would be right there, and the left-handed endpoint for the last one would be right there, okay? So for the midpoint rule, the height of the rectangle is from the x-axis to the midpoint of the subinterval. So for the last one, it was from the x-axis to the left endpoint. So what did that look like? It looked like from the x-axis to the left endpoint, x-axis to the left endpoint, x-axis to the left-hand endpoint there. So now instead of the left-hand endpoint, we're going to use the midpoint of that subinterval. So the midpoint of this first interval here is right there, and so I plug in right there to get this rectangle with a height based off of the input of the midpoint. The next one with the height based off of that midpoint input, and then the last one based off of that midpoint input. Okay? The last one, the right-handed endpoint. So with the right-handed endpoint, the height of the rectangle from the x-axis to the right endpoint, right-hand rule, left endpoint, left-hand rule, right? And so this is going to be on the right side, so I go to the right side of each interval and I plug in the input for my f to get this height here. Same thing, plug it in here to get the height of that rectangle. Same thing, right hand endpoint, I plug it in to get the height of that last right angle. Sorry, the height of that last rectangle. All right, now, whenever I'm calculating the area here for this left-hand endpoint, so this is my left-hand endpoint here, I'm calculating the area based off of finding the area of these three rectangles. How do I find the area of a rectangle? I multiply base times height. So the first one, the delta x here is the same for each of these. Each delta x is 1. But the heights are different. To get this output here, I plug a 0 into my function, okay? So that first value I plug in is my x1. So remember, this was x1, this was x2, this was x3, and this was x4. Okay, we found that when we partitioned the interval at the very first. So f of x1 outputs this height, and delta x gives me this width. So multiplying them together, you will get this area here. Now this next one here, I plug in f of x2, and I get, when I plug in x2, f of x2, I get this height here, and delta x once again is that width there. And then f of x3, I plug in f of x3, I get that height there, multiplied by the same width. So 1 times 1, so if I plug in a 0 here, I get 0 squared plus 1, which is 1. Then multiplied by my width, my delta x equal to 1. I get this area here. The next one is I plug in a 1 in here. I get 1 squared is 2. I'm sorry, 1 squared is 1 plus 1 is 2. And so 2 times your delta width of 1 gets you 2. So that second triangle has this area here, just like where those are corresponding. And the last one, when I plug a 2 in here, I get 2 squared is 4 plus 1 is 5. 5 times 1 is 5. So this area is represented by that rectangle right there. And so when I add that up, 1 plus 2 plus 5, this gets me 8. Okay? So in general, the left-handed rule for subintervals, if I take I equal to 1 and go up to 3, then I sum these values here. So literally what this is saying is that this is equal to that right there. This is a fancy way to say add a finite list of things, starting with I equal to 1. So the first time I do it, I put a 1 there. And then whenever I finish that, I go to I equal to 2. And I plug in a 2 everywhere I see my I. And then the last one is the I equal to 3. And because the last one is where we stop right there, and I see that I plug a I equal to 3 in. So just to let you know what all the pieces are in this little setup here, because this will be way more important for you in Calculus 2 when we do infinite series, which is really pretty cool. Sum symbol is this sigma here, that sigma. So remember, I told you that this elongated S was the infinite summation. This here is a finite, which is the opposite of infinite, right? So those two things are different from each other, right? This is an infinite sum. This is a finite sum. The way you would turn that symbol, the sigma, the capital sigma, into an infinite sum would be to say like I equals 1 to infinity. So, but right there, that's a finite 3. So we'll talk about that more in Cal 2. Now, this I here is known as the index of the summation. It indexes, it tells you what your I is changing from here to here. So we start at 1 and we go to 3. We start at 1 and we count up by whole numbers, natural numbers. The lower bound is told here. That's the smallest one you're going to have. The upper bound is told here, and this is the largest one. So we start at 1, we go to 2, and then we end at 3. The summand is what we're summing. So what to know from this part here, this left-handed rule here for increasing functions, okay? X squared plus 1 is an increasing function. This increasing function, the left-handed rule will always give you an under approximation. Why is it an under approximation? Look at all, like if we were going to find the area, the true area, it would be this, all of this in here, okay? Everything in here. But what are we missing with our rectangles? We're missing some pieces of it, right? So that makes it the under approximation that it is. So if it's an increasing function, very important, it's an increasing on the interval function, then the left-hand rule will be an under approximation. And you can see that when you draw the picture. Now the right-hand rule, if it's an increasing function, what do you notice? Well, it looks like these rectangles actually are going to get all of the area they're supposed to, right? Okay, so that's all of the area that they're supposed to get in black right there. But what else happened? I also got area that I was not supposed to get. So the right-handed rule for a increasing function on that interval would actually end up being an over approximation. So an under approximation here of 8 and an over approximation here, let's run through the math. So remember this was x1, x2, x3, and x4, right? So I'm going to plug in x2 to get the height of that first rectangle. Then I'm going to do x3 for the height of the second rectangle multiplied by the delta x. Then I'm going to do the x4 here for that width there, or for that height of that last rectangle. So when I do my math here, I see that that's going to give me an output of 2. Okay, so 2 times 1 gives me that first area of that rectangle. The next one gives me an output of 5. So when I plug in 5 into my function, I get 5 squared times 1, and that gives me that area, that second rectangle. And then the last rectangle has an area of 9. When I input 3 squared plus 1, 3 squared plus 1 is not 9. How did I mess that up? Okay, sorry about that. So whenever I plug in, oh, yeah, okay, sorry about that. That should actually be 10 right there, okay? 3 squared plus 1 gets me 10, okay? So 10 times 1 for the area of this rectangle here is going to be 10. So, sorry, that answer is not going to be the right number, but that's 2 plus 5 plus 10 should be 17. So just take a note of that. Make sure you keep that correct and straight in your notes, okay? So that should be 17, okay? So the sum formula here is the sum from I equal 1 to 3 of f of x sub I plus 1 times delta x. What's the difference between this one and this one? Well, if you notice, the x we started here with was x1 because it was that first one there. The x we started with here was x2 because it was that second one there. Okay, so we used those three there and we used these three here. All right, so I needed to add 1 to start at the next one instead of starting at the first one. Okay? This, once again, this is an over approximation. For the right-handed rule, if you have a function that's increasing on an interval and you use the right-handed rule, then you will always end up getting that over approximation from what the true area should be. Okay, as you can see there, it gives you an over approximation. Now, that was an over approximation. This was an under approximation. The midpoint rule, you can probably tell from geometry here. How do I find the midpoint of an interval? I add the 2 here, and then I divide by 2. And so that will get me the midpoint there. So that's exactly what I'm going to do. I'm going to add x1 plus x2, and I'm going to divide by 2 to get the average, that midpoint. So that's what that is. It's the midpoint, just like your midpoint formula. So we evaluate at that point, and we do that for each of the midpoints. Okay, so the first one, the middle, the average of 0 and 1 is a half. So I plug in 1/2 into my function. So that's the height of the first rectangle, is that f of 1/2. The next one, the average of 1 and 2 is 1.5. So f of 1.5. And then the last one, the average of 2 and 3 is 2.5. So I input a 2.5 for that one. So what is this going to equal? If I plug in 0.5 into 0.5 squared plus 1, I get 1.25. If I plug in 1.5 into this and I square it and add 1, then I get 3.25. If I plug in 2.5 into this and I square it and add it, I get 7.5. Now if I add these three things together, that's going to be the area of each rectangle. That produces 11.75. Okay, 11.75. Now, what I want you to notice about the midpoint rule is when you think about the area, that exact area from under the curve from 0 to 3, kind of looks like this right here. Okay, now what's happening? In some places, we skipped over it, right? We didn't count the actual area, but how did we make up for it? We made up for it over here because it actually counted stuff that wasn't supposed to be counted, and we made up for it over here too. So those yellow areas kind of help fill in the gaps of those X blue areas there, okay? So they kind of balance each other out. So the midpoint estimation, the approximation, is actually a better approximation than the under approximation of the left-hand endpoint and the over approximation of the right-hand endpoint for increasing functions. Remember, x squared plus 1 is an increasing function. If this were decreasing, it would literally be the opposite. Okay, if you think about it in just a picture, a left-handed endpoint would look like this. And you would see that the left-handed endpoint is an over approximation for a decreasing function. For an increasing function, it's an under approximation. And so the same thing works with the right-handed endpoint. It's the exact opposite. So the question becomes, is this the best approximation that we could get? All right, that ends up being the question. What happens as we increase the number of rectangles in? So right now, all I have are 3 rectangles, okay? So the question becomes, is that the best we can do? Is that really the best we could do? What if instead of doing 3 rectangles, I had like a midpoint rectangle for each one of these, okay? I'm not going to make it perfect, but you guys kind of get what I'm trying to do there. Would this be a better approximation to the true area under the curve? As 1, 2, 3, 4, 5, 6, n equal to 6 definitely produces a better approximation. Look at how many gaps there are compared with all the overs and unders that we had for the n equal to 3. Okay, so the more rectangles you have, the better the approximation becomes. So the approximation of the true area gets better and better. And by the way, if I do evaluate this integral here, that true area is equal to 12. Okay, we'll talk about how to do that in another video. But that area is 12. So when you look at the numbers here, 8, 11.75, and I think this one was 17, right? Because we said that that was supposed to be a 10 there. This is really close. It's really good. For n equal to 3 rectangles, we got like within 0.25 of the true exact area. That's not bad, especially for government work, right? So with the width of the rectangles, what's happening as we increase the number of rectangles, what's going to happen to that width? Well, if you increase the number of rectangles there are, then the width actually got smaller than what it was. Okay, so the widths just keep getting smaller and smaller. So the widths are decreasing. And so how do you calculate the delta x, the width of each subinterval? You take b minus a divided by n. Well, guess what? As n increases, so I have what? I have 3 over n for, that tells me how wide delta x will be, right? For this interval from 0 to 3. If I take the limit as n goes to infinity, so what am I doing? I'm putting in when I'm finding the area under the curve, what am I doing? I'm adding up infinitely many rectangles, right? That's the goal, okay? So as n goes to infinity, what are my widths doing? My delta x's are going to 0, okay? So very, very powerful statement right there. As we increase the number of rectangles, my width of each of those rectangles is limiting to 0. Pretty cool.